Hi guys, يعطيكم العافية معكم محمود. Uh, Welcome to lecture 6 of calculus sponsored by the Chain of Education. So in this lecture, we'll be talking about improper integrals in general, the types of improper integrals and some techniques to solve improper integrals. So to start with, what is a proper integral and what is an improper integral? A proper integral is simply the integral that has the form from a to b of f of x dx, okay, such that a and b are two constants that are boundary constants and that doesn't make any trouble with the function, and they are not infinitesimal. When we are solving, for example, from 1 to 2 of the 1 over 1 power x squared dx. In this case, okay, I can visualize this to be, a simple integration 1 over x squared. So if it will be minus 1 over x from 1 to 2, right? And this will yield some constant. So this is a proper integral because this type of functions yield a constant. Sorry, yes. So this type is a proper integral, and it's proper because the boundary terms I'm choosing for this integral don't cause any trouble in evaluating. I don't have infinity, I don't have zero. So at some point, what will happen if I had zero? So I will have zero here. So that doesn't work well for me. However, improper integrals are integrals of the form, for example, from 1 to infinity, 1 over x squared x. Here you see we have this infinity term. So this is an improper integral because the boundary I'm including here includes infinity, and infinity is not something I want to deal with constantly. Okay, so this is an improper integral. Or for example, if I did the integral from 0 to 2, 1 over x squared dx, this will yield also an improper integral. Those integrals are improper integrals of type 1 and type 2. But we'll talk about this later. So if we can imagine, like for proper integrals, if we had like here a and here b and here some function. Okay, sorry for this bad drawing, but we know that the integral from a to b of f of x dx, assuming this red curve is f of x, will be equal to the area under this curve, right? Okay, f of x is continuous, so it doesn't matter. However, in the case of improper integrals, so if I have this, okay, you see, this improper integral, if I want to evaluate the area, like starting here some a and ending at infinity, this means that I want to calculate this whole thing. Okay, you see, this whole thing is never ending. So if I want to have the area under the curve of f of x, this area will be infinite. Okay, so you see why is the term improper integral important? So now I'm not dealing with some constant area below the curve. I'm dealing with an infinite curve, and I'm dealing with the area under this infinite curve. Okay, this area might be infinite and might not. How? So assume this curve ends, so it tends to zero at some point. Let's say it have this form. Okay, assume that it have this form. See, it tends to zero, so it comes very close to the x-axis. So now the area is somehow constant because at this term, so for very big numbers, very big values of x, I will be adding negligible terms. So the area will not be infinity, it will be some constant. So here we can revise the concept of converging and diverging. So we say that the improper integral converge or diverge by analyzing how it behaves. If it blows up to infinity, if the area below my curve is infinite, or if it's finite, some constant. Okay, so improper integrals of type 1 is improper integrals that have infinity in the boundaries. Okay, we've seen like 1 over infinity, 1 over x squared dx, or for example, any integral that involves infinity in its boundaries. Improper integrals of type 2 are functions that have vertical asymptotes on some value in the boundary or the boundary of integration. So it may not only be the boundary, so assume minus 1 over x dx. It could be in the domain of integration. So this is my domain of integration. So it might be in the domain of integration. How come? So من minus 1 of 1 over x dx, I have 0 here somewhere in the middle of the domain, right? So I have 0. And 0 causes improper integral because for the function f of x, 1 over x, it's not defined on 0. It causes a vertical asymptote. So in this case, I need to split this integral minus 1 to 0, 1 over x dx plus 0 la 1 over x dx. This way I will have two improper integrals. However, I won't have any implicit values in the domain that my function, my initial function f of x, which is in this case 1 over x, not defined. Okay. Of course, improper integrals could be of both types. So I could have, don't know why I'm stuck on the minus 1 over 1 over x. So assume like we have minus 1 to infinity dx. In this case, you see that I have 0 and still have infinity in the boundary. So in this case, also I need to split minus 1 to 0 plus 0 to infinity. Okay, and this could be split into from 0, so assume from 1 to 1, and then from 1 to infinity. This case, I will have an improper integral of type 2, an improper integral of type 2, and an improper integral of type 1. So yes, improper integrals could be of both types. We say that mixed type improper integrals, we call them. Before moving on forward, I need you to acknowledge that what we are doing here is very important and very essential. Why? Functions have many uses. So when I'm dealing with integrals, I'm dealing with areas in main cases. However, in real life examples, integrals could be the meanings of different things. The size, the variation, it could have many implications. So I need to understand what type is my integral. So if it's a proper integral, I know that I wouldn't have any trouble analyzing it. However, when I have an improper integral, this causes a problem. And as we've seen before, that those improper integrals could converge, could diverge. So this could affect my analysis. Okay, let's move on. To solve those improper integrals, so we have infinity. I got you some shortcuts. One, let's use the symmetric domain. What do I mean by symmetric domain? So domain of integration. If my domain of integration is from minus a to a of f of x dx, and let a whatever value you want it to be, except 0, of course. So from -1 to 1, from -1 to 100, from -2 to 2, from -infinity to +infinity. This domain is symmetric. Symmetric, so I have here -a, I have here a, and I have here 0. So it's symmetric around 0. Okay, this symmetric integration, okay, I gave you here 2 examples. So if you see, I have here some value. So this is -a, and this is a, and here is 0. See, if I'm integrating this function under this from -a to a, I think it's enough for me, okay, to realize that I don't need that much integration, okay? So, because this area is equal to this area, is equal to this area, right? So if I can calculate the area of this from 0 to a, or from -a to a, I can calculate the whole area. So, and in the second case, see, this is my -a here, and this is my +a here. And those cancel each other, right? So the whole area will be 0 in this case. How to find these functions if I don't want to draw them and see that they are symmetric? Well, you need to know if the function is in an even function or an odd function. A function is said to be odd if function f of x is said to be odd if f of -x is equal to -f of x. See? And in this case, the function derivative integral -a of f x dx would be directly equal to 0. I won't bother even calculating. In other cases, okay, so here you can take sine x, for example. So sine x from -1 to 1 sine x, I can directly say it's equal to 0. And if you evaluate it, you will find this result. And in the second case, we'll have the even functions. Okay, even functions defined by f of x is equal to f of -x. And in this case, as we've seen, the integral -a to a of f of x dx will be equal to 2 times integral from 0 to a f of x dx. It's not much of a shortcut. However, maybe sometimes you don't want to deal with negative terms. Maybe sometimes you don't need to deal with positive terms. So this shortcut might help. Okay. So this is my first shortcut. My second shortcut to analyze the behavior of improper integrals is the p-integral. What is the p-integral? So we've seen before the function 1 over x. What you don't know about the function 1 over x is that although this function tends to 0, this curve 1 over x, so this curve comes very close, okay? It becomes very close to the x-axis at infinity. Yet it will not be close enough to let me avoid adding numbers. Yani, you know that the area is nothing but blocks. So if I want here, I can divide it. So if I want to divide it into small blocks. So the function 1 over x, or any function with the power less than 1, okay, 1 over x power p, such that p less than 1. The behavior at infinity will be that, okay, reminder, the integral is the sum of these small rectangles that I chose. So the behavior at infinity will be that the limit of this function is equal to 0, and that's right. However, the curve does not come very close to the x-axis in a way that allows me to constrict my area finally. So in this case, the improper integral will diverge, right? Because I will keep adding and adding and adding and adding rectangles. So the area will keep growing and growing and growing and growing. So it will reach infinity at some point. However, if we take 1 over x squared, for example, this function is much faster. It tends to 0 much faster, and any power that's greater than 1. So the curve comes very close to the x-axis in this case, and I can stop adding. And this is why I say that in case of me having the integral from a to infinity of 1 over x power p, it's enough for me to know the behavior of this improper integral, type 1 improper integral, which is convergent if p is greater than 1 and divergent if p is less than 1. This is all for today. Thank you for your time. Study well.